So in part 2 of topic 11, I'm going to specifically focus on the subtopic 11.3, which is using analytical and spectroscopic techniques to identify organic and inorganic compounds. So the resources that I use for this topic is the Oxford Study Guide, your chemistry textbook, the SL edition, Brown and Ford for the Pearson, the Cambridge textbook, 2014, and the IB Chemistry Question Bank and your IB Chemistry data booklet. So here's a bit of a review of what was in part 1. So when we look at spectroscopic analysis, we're looking at 4 things. We're looking at the index of hydrogen deficiency, IHD. We're looking at the infrared spectroscopy, which we looked at in the previous part. The IR, a reminder, is the identification of bonds and functional groups. It only tells me what kind of bonds there are. It doesn't tell me anything about how many hydrogens I have, how many carbons. It's just the type of bond that I have. And when we talk about the index of hydrogen deficiency, we just look at the presence or absence of double bonds or whether I have a cyclic molecule. Here we're going to focus more on the mass spectroscopy in part 2, and we're going to look at more nuclear magnetic resonance as well. Also a summary for the infrared spectroscopy. This is section 26 of your IB data booklet. And this is very important, and it's a good idea to actually go over these before you actually go into the exam and when you stop studying topic 11, because it gives you really important information about what you actually have in a molecule and what to look for when you have an IR spectrum. So if you can look at all the bonds that you can have and where they're actually absorbing at and the intensity of these peaks, then you're halfway to solving these IR spectra. So the common ones to look for are the carbonyl group, which is always found in aldehydes, ketones, carboxylic acids, and esters. And it's a very strong peak at around 1700 to 1750. Another thing that you can be looking at is the OH. And now the OH can be found in 2 places, depending on the type of molecule that you have. If you have a carboxylic acid, then this is going to be a strong, very broad peak between 2500 and 3000. But if I have an OH that is found in an alcohol, then that's going to be at 3,200 to 3,600. So be very careful when answering these questions. If you have an alcohol, look for this here. And if you have a carboxylic acid, then you look for this one here. And there's the amines and the CH strong peaks for alkanes, alkenes, and arenes as well. Usually in the questions in the exam papers, they tell you which regions to look for, but it's also a good idea for you to look for these as well. Now, looking into mass spec. The mass spec is basically what we use in order to find out the fragments, the fragmentation of the molecule. And this happens because what we do is we take a sample and we inject it into the mass spectrometer. And when we do that, we hit this molecule with really high intensity electrons, which knocks electrons from the molecule, making it into a positive charge. So therefore, it loses these electrons. And so the ionized or positively charged molecule then passes through the mass spectrometer and it basically breaks apart. So if you have a hole, then it just fragments into smaller bits, and each bit is going to basically absorb at a specific region in the mass spec, which is what I'm going to show you in a minute. And this is called the fragmentation pattern. The peak with the largest mass is that of the parent atom. So the last one that you see in the mass spec is going to be the molar mass of your molecule. And each time you go to the left of it, you're basically removing a component from the parent atom or the parent molecule. Why are fragmentation patterns important? Because they provide structural information about the molecule. They provide evidence of the presence or absence of molecules. And we usually use it in forensic sciences to find out information about a crime scene, etc. And it's also used a lot in sports events to deter drug cheats from using banned substances to enhance their performance. It also can be used to distinguish molecular isomers. So the best way to explain what a mass spec is to actually show you. Now, you know this before from when we were talking about topic 2 with the relative atomic masses and the molecular masses. But this is how it comes together when we have an actual molecule. So you can see here I have ethanol. Why is it ethanol? I have 2 carbons, that's eth, and ol, because it's got an OH group, which makes it an alcohol. Now this is its spectrum here. You can see that I have 1, 2, 3, 4, 5 peaks. This last peak here, which is 46, and it doesn't have to be the highest peak, okay, is the molar mass of the molecule. So if you count 15 and 31, you would get 46. So this automatically gives you the molar mass of the molecule. So always pay attention to the last peak that you see. And every time you go to the left, like I said, you are basically losing something. So if I drop from 46 to 45, that tells me that I've lost the hydrogen. It's the only thing that's 1 unit, okay? So then I see these other peaks here. I see a major peak at 31. I also see a peak at 15. Now, the peak at 15 tells me that it's a methyl group. And I know this, and I'll show you in the next slide, because in your data booklet, you also have a list of all the molecules that would have a specific fragmentation that you would be looking at. And at position 31, okay, or at peak 31, this is indicative of this molecule here. So this is in your data booklet again. Whenever I lose a fragment, it's going to have a specific mass lost, okay? So this is my methyl, and if you count 12 plus 3, this is going to give you 15. If you see a peak at 45, then the examiner wants you to understand that this is of a carboxylic acid, okay, the COOH group. So like I said, use this as like fingerprints, which they are fingerprints, for the fragments that you might have. A molecule with an empirical formula CH2O has the simplified mass spectrometer below. Deduce the molecular formula and the possible structure of this compound. So here you can see that I have here a formula. This is the molar mass, which is at 60. I have peaks at 45, I have peaks at 43, and I have a peak at 15. So I can tell you here that I actually have a methyl group. I also have the peak at 45. And as you recall that if I have the peak at 45, then that's basically telling you that you have a carboxylic acid there. So you can deduce what the molecule is just by looking at the fragments that you have. Proton nuclear magnetic resonance, proton NMR, okay, or 1H NMR, looks a bit complicated, but it's very easy, okay, because it's always telling you the amount of hydrogen environments that you have. So basically, it gives you the complete structural information about a molecule. So as the name suggests, the proton NMR gives information about the hydrogen atoms within a molecule. So how does it do that? So what I'd like you to think about is that some atoms are able to produce resonance because they act like little magnets. So the protons, as this is the isotope we're looking at, remember a proton means that I have one proton in the nucleus. That's the specific type of a hydrogen. There's other isotopes as well, but the proton is the one that we're specifically looking at. Acts like a tiny magnet because they have a spin. And what a spin means, it can point up or it can point down, okay? So if it is exposed to an external magnetic field, like the nuclear magnetic field, which is basically what we're using here, it will align with the magnetic field as the same way as a compass needle will always point north or against it. So here you can see that the hydrogen is aligned with the magnetic field. This is a lower energy, or it can be aligned opposed to the magnetic field, which means that it's got a higher energy. You can see here's my energy levels. So the more energy I require to change the resonance or to flip the actual spin means it's going to be at a higher energy level, okay? So energy in the radio frequency range of the electromagnetic spectrum, which is basically what the NMR uses, and this allows it to happen. So I think you're familiar with MRIs in the medical field. That's the scanners. This works in the same way, but it's in the lab, and it's specifically looking at the proton NMR. So how exactly does an NMR work? So you can see that here I have a methanol carbon with 3 hydrogens and an OH. If I look at the pieces of this, I can see that these 3 hydrogens are the same. They're on the same carbon. And this hydrogen is different because it's connected to the OH. So I can see that these are 2 different hydrogen environments. So a proton is affected by which atom is attached to it. This is called the chemical environment. So think back to when we were talking about electronegativity. Think back when we were looking at covalent bonding, where you have the polar and non-polar due to the electronegativity differences. So here we have a carbon. It's got almost the same electronegativity as the hydrogen, so the electrons are going to be shared equally. But here, the oxygen is going to be more electronegative, so the electrons are going to be closer to the oxygen. Now, what does this mean? This means if I wanted to shield the electrons of the hydrogen from the magnetic spectrum, okay, it'll be harder to shield them from something that is equally shared than from something that is unequally shared. So this is why these will basically have different chemical shifts because of their electronegativity. So the chemical shift provides information about the environment around all the hydrogen atoms in the molecule. And this is dependent on the type of element bonded to the hydrogen atom. So the chemical shifts are directly proportional to the number of chemical environments that you have. And the symbol for chemical shift is this delta sign, and its unit is ppm. So when we put the sample in the NMR spectrum, okay, we need to have a reference point. That reference point is called tetramethylsilane. This is my silane in the middle, and this is tetramethyl. As you can see here that this methyl is the same as this methyl, is the same as this methyl, is the same as this methyl, which means that I see only one peak in the NMR spectrum. And why do we use it? Because when you put it, we use it as a reference of 0. So when we put our sample in, we can basically see how much is shifted from the TMS. And TMS is its abbreviation. The third terminology that I'd like you to understand is the integration trace, which indicates the relative number of hydrogen atoms in the two environments. Now, I know this sounds like a lot of information and a lot to take in. So let's look at a real proton NMR spectrum to show you. So here's an example of an aldehyde. I can see that this is an aldehyde because this is my carbonyl group here, and this is my hydrogen atom. And the other side of the carbonyl group, I have a CH3. So how does this link to here? So here you can see the TMS. Here you can see my chemical shift, parts per million on the x-axis. And here you can see my absorption. So this is basically what a proton NMR spectrum looks like. What you also see is two peaks related to the molecule. Again, the TMS is the reference, which tells me that I have two hydrogen environments. And if I look back to the molecule, I can see this. So I see 3 hydrogens connected to the same carbon, which means that they are the same environment, and a second hydrogen that's connected to the carbonyl group, which means it's different to the other carbons, so that's my second environment. The other thing that I can see from this spectrum is the peaks. So these are my integrated traces, which means that the area under the peak tells me how many hydrogen atoms that I have. So if I was to compare this peak with this peak, it's in a 1 to 3 ratio. And if I look back to the molecule, I can see that it's in a 1 to 3 ratio. I can also see that depending on what the hydrogen is connected to, it'll either be downfield, okay, which is that way, or upfield, which is that way. Downfield means that there's not a lot of shielding because it's close to an electronegative element, which means the electrons are closer to the more electronegative element. That's why it's called downfield. Or it's going to be upfield, which means that it's close to an element that is not so electronegative like carbon, and that's going to be closer to the 0. Okay? So I can easily relate these peaks to my molecule. So here, if I have 1 hydrogen, that's easy. This is this hydrogen here. And if I have 3 hydrogens, then this is easy also because that means that it's related to this hydrogen here. Building up from the previous example, again, I have an aldehyde, but this time I have 3 carbon atoms there. One for the carbonyl group that's attached to the hydrogen, and then a second environment where you have the CH2 here, and then a third environment where I have the 3 hydrogens there. So a tip here for these kind of questions is always circle or highlight the hydrogen environments that you have. So anything that's on the same carbon or the same atom, treat it as one environment, okay? So here again, this is going to be my TMS. It's not shown in this graph, but we know that it's there because it's always the reference. And again, I have 3 peaks. So this is going to correspond with the 3 carbon atoms, 3 hydrogen environments that I have. And so I can clearly see that this is this carbon here with the 3 hydrogens, and this is this carbon here with these 2 hydrogens. And again, because this is an aldehyde, I see it furthest downfield with 1 hydrogen there. So these are other examples as well of ethyl ethanoate and of ethanol here again. So here you can see both of them have the references there, and you have got the integral peaks. And so the hydrogens that are closer to the more electronegative elements or closer to the carbonyl groups are going to be more upfield towards that side as to downfield there. The key points here, if you are given the molecule, first of all, determine the number of hydrogen environments. This is really important because once you figure out how many hydrogen atoms that you have, how many environments that they belong to, then it's really easy to identify the peaks that you have, okay? Because they're related to each other. Use the integration trace to determine the number of hydrogen atoms under each peak. Use your IB chemistry data booklet to identify the peaks. I can't stress on this enough because that's basically your fingerprints, okay? And finally, remember, if a hydrogen element is bonded to electronegative elements, the peaks will be upfield, closer to 10, and closer to 0 if they are bonded to carbon or less electronegative elements. So let me go through this first. So this is basically what the NMR data that you have in your chemistry data booklet. Again, you don't need to memorize these values, but you do need to know what it means when you have a certain chemical shift. So when we saw before that we had a CH3 group, okay, when it wasn't associated with anything next to it except a carbon, it'll be around this region here, okay? But if we had something like an aldehyde hydrogen, that is going to be between 9.4 to 10. So just be mindful of this data booklet because it really helps you in identifying these shifts. What if I'm not given the molecule? Again, this is really easy because if you're not given the molecule, the first thing that you should be doing is using your chemistry data booklet. Think about the number of peaks is the same as the number of hydrogen environments that you have. So if I have 3 peaks, that tells me that I have 3 hydrogen environments. If I have 4, then I have 4. If I have 1, then I have 1. And use the integration traces to determine the number of hydrogen atoms. Okay, so the total number of hydrogen atoms under each peak is going to tell you the total number of hydrogen atoms in the molecule. So that gives you an idea of how many hydrogen atoms that you should have as a total in the molecule. So here is an example from your textbook. The proton NMR spectrum of X with molecular formula of C3H6O is shown below. So here I can see that I have 3 peaks, and that tells me that I have 3 environments. What it also tells you is the integration traces or the integrated traces. So here I have 1 hydrogen, here I have 2 hydrogens, and here I have 3 hydrogens. Okay, so that means I have 3 environments that I need to look at with this integration there. So if you look at what you have here, this cannot be because that tells me that I have only 1 environment. Okay, here I have 1, 2, 3, so that could be an answer. And here I have 1, 2, 3, 4, so that can't be the answer. So the only logical answer to this one would be option B, which again tells me that I have an aldehyde. This is the CHO bit, this is the CH2 in the middle, okay, and then you have the CH3 at the end. And if you count the number of carbons that you have 1, 2, 3 carbons, and you have 3 plus 2 is 5, plus 1 is 6 hydrogens and 1 oxygen. So this gives you the clear answer there. So in the next slides, I'll be looking at piecing it all together in terms of using the proton NMR, the IR, and the mass spec to identify molecular molecules. And in order to do that, I'm going to be using the IB question bank to help solve these kind of questions. So let's look at some questions from the IB question bank. I've selected these following questions because I thought they are a good reflection of how IR, NMR, and mass spectra can be used either to identify functional groups in a molecule, if you're given the molecules, or to prove that I have a certain molecule. So this question says the following spectrums show the infrared spectra of propan-1-ol, propanal, and propanoic acid. I've intentionally made the screen small so you can see all the 3 spectra together. Now, how do I analyze such a question? The first thing that you need to do is recognize what kind of functional groups that you have. So first up, I have propan-1-ol. Propan-1-ol tells me that I have an alcohol. So in this case, I must have an OH group that is attached to 3 carbons. What I shouldn't have with the alcohol is the presence of the carbonyl group, which is a CO double bond. Okay, so then I need to look at a spectra that only has the OH. Propanal is an aldehyde. An aldehyde means that I have a carbonyl group that is attached to a hydrogen on one side and an R group on the other side. Now, given that this is propanal, that means I must have 2 carbons and hydrogen groups on either side of the carbons. Okay, propanoic acid means that I've got a carboxylic acid, so I must have a carbonyl group, and I must have an OH group. And again, because it's propanoic acid, I must have 3 carbons, including the carbonyl carbon, so that means that I must have another 2 carbons there, with the hydrogens obviously around the carbons. Okay, so what these tell me is that propanal and propanoic acid both must contain the carbonyl group. In addition to the carbonyl group, the propanoic acid must also have an OH group. Okay, and both of them should have the CH sharp bend or sharp peak as well. Whereas the alcohol, on the other hand, shouldn't have the carbonyl group. Now, if you don't remember what I'm talking about, you need to go back to the chemistry data booklet. When I look at the chemistry data booklet, then I can see all of the bonds that I'm interested in and the actual organic molecules or the functional groups that I have, the wave numbers that they actually absorb at, and their intensity. So when I talk about a carbonyl group, I'm talking about this part here. And where I should see it is in the region of 1700 to 1750, and I should have a really strong peak there. So if I go back to my molecule and I look at the first spectrum, I don't see this in the first spectrum, but I do see it here in the second spectrum, or spectrum B, and I also see it in spectrum C. So that automatically means that spectrum A must be that of the alcohol. And what also proves to me that this is the alcohol, I see a very broad peak around here. And if I go back to my data booklet, if I have an OH and an alcohol, then I should see it in the region of 3,200 to 3,600, and it needs to be strong, but also broad. That means it's not sharp, like you see it for the carbonyl group, but a broad peak, as we see it here. So it looks like this. Moving on to spectrum B, I need to see which one of them is going to be my propanal and the propanoic acid. Again, with the propanoic acid, not only should I have a CO double bond, but I must see the OH band. Now, if I go back to my data booklet, I have 2 OH groups there. I have one that's for the alcohol and another one that's for carboxylic acid. And what you should see there is in the region of 2,500 to 3,000. And it should be a strong and also a very broad peak, as opposed to the broad and strong peak of the OH of the alcohol. So if I look at the spectrum here, you can definitely see that this is a very broad, it's much broader than this, okay, and very strong peak. And it's in the region of 2,500 to 3,000 wavelengths, okay? So this must be my propanoic acid. Finally, spectrum C, you can see that I don't see any broad peaks here, but I still see the carbonyl group. So this tells me that this must be my propanal. So this question here, identify each compound from the spectra given, use absorptions from the range of 1700 to 3500, and explain the reasons for your choice, referring to section 26 of the data booklet, which is basically what I said. So here is what they say in the mark scheme. Okay, like we said, that the first one is going to be my propan 1-ol, spectrum A, and that's because I don't have the carbonyl group. So you can talk about the absence of the carbonyl group and the presence of the hydroxyl group or the OH group in alcohols, but you must specify that this is in the region of 3,200 to 3,600 reciprocal centimeters. Okay, so it's really important that you are very specific about what you're talking about. Not only do you say what you see or don't see, but you have to talk about the range that you're supposed to see them or not see them. The second spectrum is that of propanoic acid. Okay, so here are your options to prove that it's propanoic acid, that you have a carbonyl group and a hydroxyl group in carboxylic acids. Okay, and you must state that they are in the region of 1700 to 1750, and that's for the carboxyl, so the carbonyl group, and that it's at 2,500 to 3,000 reciprocal centimeters for the alcohol. These are alternatives that you can talk about. You can say that the OH in the carboxylic acid and 2,500 to 3,000 reciprocal centimeters in the range, or strong broad peaks at these ranges as well. For me to get the perfect answer each and every time, I would like alternative 2, where you basically talk about the specific functional group and where it's actually absorbing at, because then it's very clear to the examiner that you know what you're talking about, especially that the question is asking you in the regions that you see them. The final spectrum is that of C, okay, which is the propanol, and you can talk about the presence of the carbonyl group, and you can also talk about the absence of the OH group, whether that be for the carboxylic acid or the OH for the alcohol. So this is how you get the answer to those kind of questions. The next question is looking at the mass spec. So it says combustion analysis of an unknown organic compound indicated that it contained only carbon, hydrogen, and oxygen. Deduce 2 features of this molecule that can be obtained from the mass spectrum. Use section 28 of the data booklet. Now the important thing here is to basically look at what you see here, but also continue on to see what they're actually asking you. So what they're actually asking you is for these specific regions, okay, or these specific peaks that you see in the graph. So when you look up here, 58 is this peak here, and 43 is this peak here. And they're asking you to use the data booklet in order to identify what you actually see there. So you go back to the data booklet and you go to section 28. So this is the NMR, and then this one is the mass spec. So the important thing to know is that any time that you have a peak at the end, this is going to be for the molecular formula. Okay, so this is actually going to be for your compound. Okay, so this is the actual molecule, the M+, if you want to, the molecular ion. And then you have to work out what the 43 is. So in order to do that, the easiest way to do that is to say, okay, I have 58, which is the actual molecular formula of my molecule, and subtract 43 from that. And when I subtract these from each other, I should get around 15. So when I go to the mass spec, 15 tells me that I've actually lost a methyl group. So that peak there that I see here, okay, is my molecular formula minus the CH3 that belongs to this molecule. So when we go to the mark scheme here, like I said, mass to charge ratio of 58, which is the last peak that I see, is the molar or the relative molecular mass or the weight or the MR. Any of these things are correct, and it's the 58 grams per mole. And the MZ of 43 simply means that it's my actual fragment minus the methyl group, okay? So they say that it loses the methyl group at this point, or it's got COCH3 plus. That means that you've understood that it's basically lost CH3. And it also goes on to explain what I cannot penalize you on as an examiner. So I do not penalize missing charge. So if you forget to write the charge, remember that when we're talking about the mass spec, they have to be positive ions. And I can accept molecular ion peak, which is this one. If you know from what you have that this is going to be the molecular formula, then you can talk about this. And you can accept any C2H3O plus fragment, which is either this or this. Continuing on with the next part of the question, identify the bond responsible for the absorption at A in the inferred spectrum. Use section 26 of the data booklet. Here we're going back to the IR, and they're telling you to identify this peak here. Well, this peak is very easy because we already know that this is going to be my carbonyl group. Okay? So this is basically the answer. Carbonyl group, or accept a carbonyl, the name, or a double C bond. I would actually prefer you to either write this or to write the name. Next part, deduce the identity of the unknown compound using the previous information, the proton NMR spectrum and section 27 of the data booklet. Okay, now what we know so far is that I have a molecular formula from the mass spec. Okay, if we go back up, that it's 58. Okay, I also know that it's got a CH3 group. And what I also know is that it's got a carbonyl group. So these are pieces of information that I know. And like I said, it's like a puzzle trying to figure out what I have. What I also can find from the IR is that in order to see whether I have an carboxylic acid, now I know that it's a carbonyl group. If I have a carbonyl group, there's four options that I might have. I might have a ketone, I might have an aldehyde, I might have a carboxylic acid, or I might have an ester. Okay, so for each of them, I would have to see another band to say basically I have it or I don't have it. So I can clearly see that I don't have a carboxylic acid because I don't see anything that is transmitting here. Okay, so I know this from the IR and I can keep it in mind for what I see the proton NMR. Now we'll look in the proton NMR. Okay, what do you see here? I only see one signal. And anytime you only see one signal, that means that this molecule has to be symmetric. Okay, so now I know that I have a carbonyl group. Okay, and I also know that I must have a CH3 there. Okay, so what way can I make this a symmetrical molecule? The only way I can make this a symmetrical molecule is if I see another CH3 there. That means that the left side is the same as the right hand side. And also you see that most of these are in the same position, which is in this position here, and they've been shifted by something that's slightly electronegative. So when I look at the mass spectra, the IR spectrum, okay, right, so this is for my ester and this is basically for my ketone. So if I look at the region, I see that it's between 2.2 to 2.7, and if I look back, I see here that it's between 2.2 to 2.7. So this must be my molecule. Right? So information deduced from the proton NMR is that I have one signal. So that means that I have a symmetrical structure. I also have a chemical shift of 2.2, so this indicates that I have a hydrogen, okay, on a carbon that's next to a carbonyl group, okay? So where did they get this from? They got this from here, okay? So this is basically listing all the types of protons that I must have and all the chemical shifts that I have. So you just have to basically figure out where your chemical shift arises and what kind of structure that I have. And if you look at this is propanone, and this is basically the structure that I drew here. Okay, so this is my carbonyl group that I saw in the IR spectra, and it's completely symmetrical because the left hand side is the same as the right hand side, which is why I only see one signal in the spectrum. It also shows me that I have nothing in this region here where I must see an OH if it was a carboxylic acid. And also if you look in the other regions, if I did have an ester, this would be my ester here, which should be in the region of 2 to 2.5, but in this case it would not be a symmetrical molecule. So this is why I can rule out this kind of functional group as well. Here's another question. Ethine reacts with steam according to this equation here. So C2H2 gas with water in the gaseous state, which is steam, gives C2H4O. Two possible products are this. So this product here can be of two isomers. And you can see that these isomers are not the same, but they have the same molecular formula. Here you've got the two carbons, you've got 4 hydrogens and 1 oxygen, and here you've got 2 carbons, 4 hydrogens and 1 oxygen. In this case, this is an alcohol. In this case, I have a carbonyl group with a hydrogen on one side and a methyl group on the other side, which makes this an aldehyde. The IR spectrum and low resolution NMR spectrum of the actual product formed are as follows. So this is my IR here, and this is my proton NMR. And the question is asking me to deduce whether the product is A or B using evidence from both of the spectra and using section 26 and 27 of the data booklet. So the first thing that I need to recognize is the difference between an aldehyde and an alcohol. The aldehyde would have the carbonyl group, but it wouldn't have the OH group. Whereas when I have the alcohol, I would have the OH group, but I wouldn't have the carbonyl group. So the first thing that I would do is I would look at these peaks there. So the first thing that I can recognize is I have a very strong and sharp peak, okay, at around 1700. This automatically makes me think that I have a carbonyl group. I also don't have a broad peak in the 3000 region. So if I go back to my data booklet and I go back to the IR, I can clearly see that I have my carbonyl group at 1700, but I'm missing this peak here for the alcohol, which is around 3200 to 3600. So this clearly tells me that I must have B from the IR. To further prove this, I'll look at my NMR, and what I see is I have a peak here and another peak here. So when I look at my proton NMR this time, okay, I would clearly see that I have a carbonyl group, okay, which is going to be around my 2.2, okay, region. And what I also see is another hydrogen group, okay, right at the end. Okay, so if I keep looking down, I would see my aldehyde there, which is in the region of 9.4 to 10. So if I go back here, this would be my carbonyl group with the hydrogen. Okay, whereas the other peak here, this will be for the CH3 component that's going to be attached to my carbonyl group. Okay, so you can clearly see here that I have two hydrogen environments, one that belongs to the CH3 and one that belongs to the hydrogen that's on the other side of the carbonyl group. What I also see is that they must be in a 1 to 3 ratio. So from the integration, I can see that they're in a 1 to 3 ratio. I have 3 hydrogens here for the CH3, but only 1 hydrogen here. So both of these information confirm to me that this must be my B product. Okay, so if we look at the answer, okay, so the identity of the product according to the IR is B. I do see a band, okay, at 1700 to 1750, which is the carbonyl group. Okay, so I must mention both, that I have this band and that belongs to the carbonyl group. I don't have a band, okay, at the broad peak of 3200 to 3600, which is basically for my OH group. And when I look at the NMR spectrum, okay, I see two signals, okay. I see a signal between 9.4 to 10, and I see another signal between 2.2 to 2.7. The 9.4 to 10 is the proton of an aldehyde, and you have to be very specific that this is my aldehyde. And the other option here, or the other signal here, is that of a proton of an alkyl group, which is next to a carbonyl group, okay? What you can also say is the other options as well, that the signal 2.2 to 2.7 is the hydrogen or the proton of that functional group there, which is basically what you're saying. Or there's no signal around this region, or that there's another, the absence of the OH signal, or whatever you want. But for me, I would always talk about what I actually have. So the giveaway here is I have this one here. This is specific to an aldehyde, this hydrogen there, at this peak there. And then this one is going to be my alkyl group, which is the CH3 next to the carbonyl group. And I hope that was helpful.